As we go into Chapter 3 now, we're taking a look at Topic 1, Relations and Functions. Here I'd like you to take some background notes on some key words that we'll be using throughout this section as part of the objectives, and that is relations. Now, what does this word mean? Well, somehow something is connected to something. For instance, members of a family are relations. But in math, we're thinking of things that are somehow connected. And one of the best examples of this is the ordered pair. We know they are definitely connected from our previous chapter. Okay, another key word that we're going to use a lot is domain. What does domain refer to? Well, in the ordered pair, it's the X element. That is the domain. And we'll give you some examples of this as we go on. How about the range? Well, these are the Y elements. Now, you might say, how would I ever remember that? Well, if you think of domain and range alphabetically, D and R, then the X and the Y also are alphabetically related to them in a sense. Now, function. This in a very simplified form is that in a relation, if the X element is only used once, then what you're looking at is referred to mathematically as a function. So take a moment, pause, and write this down. You want to know basically what these words are as we go through this lesson. And if you'd like to read it, it's available here. I'll go through it slowly. And then background also to all of this is the set theory. And again, what is a set? Well, a set was a collection of objects. In most cases, we're dealing with math items, numbers. And we write sets using braces. And we separate the members of the sets by commas. So in example 1, they want you to write in set notation the elements of this set. So as we go down a little, taking out our first element of each of the ordered pairs, there's a -4, a 6, a 0, there's another -4, and then there's pi. Now in set notation, if something is repeated, we only write it once. And there is our set of domain elements, the first letter or number in each of the categories. Now the range, let's do that in blue, would be a 2, a -1, a 0, a 0. Now it's repeated, so we don't write it twice. And then this one is pi that's squared. And there you see it in set notation, the range. All right, so this is rather straightforward, knowing the definitions and applying things. Now I've made the screen a tad smaller. So notice we could plot all of these ordered pairs. And you might say, where is pi and pi squared? Well, pi is about 3.14, which is about there, and if you squared it, it would be up around there. So this is this point, just as a little aside here. Now, in part 2 of example 1, we're asked to look at this equation, and I'll go back to red. And this is it on the graph. So we're asked to define what would the domain of this be and what would the range of it be. Well, domain, again, are x elements. And since this arrow here indicates this goes off to negative infinity in this direction and positive infinity in this direction, for x values, our domain is from negative infinity to positive infinity. And the range would be y values, and this eventually goes down as well, and this goes up as well, and that is also negative infinity to positive infinity. So you might think of any graph that is positive slope would have these values, and also if it's negative slope would have these values. And just to add a little bit to it, if we had a horizontal line, the domain would be from negative infinity to positive infinity, although the range now would just be the one value 4 here. And I believe they use giving it as a set of numbers. Here this is in interval notation, this is in set notation. In example C, we have this rectangle defined by these points. It's a parallelogram. And we're wondering, what would the domain of this be? Well, if you project this line down to the x-axis, you can see it starts at, and we're using a bracket to indicate -1 is included, and it goes up to a +1. And for the range now, projecting this line to the y-axis, starting there and going down to there, this would be a -2 to a +2. And that's what they're saying here. And this is an interval notation. Now, as we look at item D, it's very similar to the one above, but now it's shaded. So what they're saying here, it's not really the same. The domain and range would be the same, but this includes so many other ordered pairs in here as well. So just make note of that. And then in E, they're saying, although we will almost never encounter relations in the text that do not consist of ordered pairs in real numbers, there is nothing in our definition to prevent us from considering exotic relations. Take a moment to read this, and again, we're not going to encounter these, but that is a possibility. Now, in this section, we're going to take a look at functions and the vertical line test. Let's raise it up. Now, we have said what a function is. Something is a function if the x element in a series of relations is only used once. If the x element is used more than once, then it's not a function. And for this, we get to use what is called the vertical line test. Now, what is the vertical line test? Well, let's make a vertical line here. And if we take that line and pass it over a graph that we're considering, in this case, this parabola, the blue parabola, does this line intersect in this blue graph in more than one place at a time? Well, as it reaches here, it's once, and the answer is yes. It only intersects in one place at a time as you pass it over the surface of the graph. So it passes the vertical line test. It is a function. Now let's go down and take a look at this one. Well, this is a sideward parabola. Does this parabola pass the vertical line test? And the answer is no. When it gets here, it's intersecting in more than one place. So this is not a function, and we've determined it by using the vertical line test. Now, in a sense, what are you saying? Well, here, there is a value of -3 used. Also for this point. So the -3's of the x-axis are used more than once. All right. And in example 2, we're asked, is this graph of these points a function? Well, notice if you had the vertical line here, it would intersect twice. That is, the -4, which is an x value, is used twice. So this would not be a function. And how about a line with positive slope? Is that a function? Does it pass the vertical line test? And the answer is yes, it passes it. So all linear equations of positive slope, of negative slope, of horizontal slope, all would be functions. Which one would not be a function of the lines? That vertical line that we said, and I didn't draw it well. But of course, when the vertical line test went over, it would not pass. It's intersecting in an infinite number of places. So the vertical line is not a function. Now in example 3, we're looking at this graph. If we plot these points, and notice you can actually tell whether something's a function if you look at the x elements. There's a -3, -1, 0, -2, -4. Are any of these values repeated? And the answer is no. So this is a function. All right, let's go down. Now as we look at this one, just looking at the graph, does it pass a vertical line test? No, this is not a function. And we did say a parabola was when it opens upward or downward. If it opens up sidewards, it's not a function. Now, in this section, we're going to take a look at what is called function notation and then function evaluation. Well, the symbol for function is an F, and then it's written with a parenthesis and usually with an X like so. Now, other letters can be used, but it's this symbolism that's used to represent a function. And then usually you have some sort of rule here that you're going to input into this rule some value of x. Now be careful, this does not imply multiplication. Often parentheses imply that, but here it's not. So whatever value of x you then put into the rule, and that is the evaluation of what we have. And that's what they're describing here. And let's go down and just look at some more. And you can see it in some detail. Again, if you want to go to the Learn and look at this, it gives lots of information. And here they're introducing perhaps the greatest mathematician of all times, and that's Leonard Euler. And you'd think you'd pronounce it a different way, but it's E-O. That in German is pronounced as an O. So Euler, Leonard Euler, a famous mathematician who developed the f of x as a function notation, and also the letter I for imaginary numbers. And one of the other famous things attributed to him is the letter E, which I often refer to as Euler's E, although he personally didn't name it that way after himself. He has a number of things in math named after him. If you ever do a Google search of Euler, you can see the many contributions that he did to mathematics. Now, in example 4, they're asking us to rewrite these A, B, C, and D mathematical statements in function notation. And I'm going to give you a little simple shortcut in many cases, that wherever there's a y, the function symbol can be substituted for that. And for this, let's just follow what's written here. I'll do it slowly so you can take some notes. They do a good job. So for letter A, you might say, how would I write that in function notation? Well, I'm just going to replace the y with the function symbol. Now, they'd like you to also evaluate this where our x value, which is in this case a -3, is to be put wherever there's an x in the system. Well, there's an x, so we put a -3 there. This becomes then a -1 plus 2 equals, as your output, a 1. And something useful that I've seen in other books and courses is this little flowchart here, where our x value is the input into the rule. Again, this part is the rule, and then you get an output, which is your value for y. So input into the rule of x. X is often referred to as our independent variable, and the y is a dependent variable. Depending on what x is, determines what y will be. Okay. All right, let's clear this up and go on. Now for part B, what we'd have to do is solve this equation for the letter y, which is what they're doing here. And then finally they get y is this, and this is in slope-intercept form. Remember, we can just change the y to our function symbol, and what they're doing here is changing it to g of x, using another letter, which they are allowed to do, especially to distinguish if functions are different. All right, let's go on. And before we do, we should put a 3 into the system, which is a negative 3, I should say, and they work it out. So our y value now is a negative 17 halves. So in a sense, our ordered pair, because this was the x, negative 3 comma negative 17 halves. A lot of this at this stage ties into what we did in the previous chapter. Now in letter C, again we have our equation. Take a moment to write it down. You want to solve for y. So you're just going to transpose that negative 5 to the other side where it becomes positive. And then we're going to replace the y, in this case, with the letter h of x. And now we've put it in function form. And now for our x value, we're going to use a negative 3. So we put a negative 3 into the system, square it. That's 9. 9 plus 5 is 14. Okay. In letter D, we see we have a radical sign in there, but we still want to solve for y. So we're going to take the radical, bring it over to the other side where it becomes a negative, and then we're going to divide everything by a negative 2 here. Notice how it changes the signs, and we substitute our y now, going back to, I guess they're using j of x. Now, they're saying our x value is a negative 3. So wherever there's an x, we're going to put a negative 3 in there. This becomes a positive 4, which is 2. And this is a negative 3. And 2 over 2 is a 1. So this became a negative 2. All right. And again, the ordered pair, this is our y value, is a negative 2. Our x value is negative 3. All right, let's go on to our next part of this. In example 5 now, they're asking us to interpret these functions from this particular graph. So we'll raise it up a little bit and make it a little bit bigger so you can see each of these as we go along. And for examples like this, I would suggest you make a little t-chart that we have here. And then it makes it so much easier. So what is the value of f at 0? So here, x is going to be 0. What is the value of x at 2? And then which one is x when, again, this is y equals 2. So now it's just going to the graph and picking things out. And I'll do this in black. So if x is 0, right here, y is going to be negative 1. If x is 2, right here, I see over here they have these units as 1, 2, and here this is 0.51, 1.52, so that's a little confusing, but it's this 2. Y is going to be 4. And if y is 2, right here, actually we have two values. We have again, this is going to be a negative 1 here. And we have another value. If y is 2, it's going to be a 3. And there are the answers. Let's check it out here below. And we are correct. Now in the text, they're giving us caution here that when we write the function symbol, again, it's not multiplication. This is just using symbols for something else. It's the value of what x is. Continuing and on to example 6 now. It says we're given this function. Now, once again, we have an x value that we're going to input into a rule, and then we're going to get an output, which would be what our y equals. So keeping that in mind, let's do this first one here. Here, we're going to substitute an a where the x is. So this is pretty straightforward, and we'll use the book here. So we're just going to replace the x with an a, so it becomes 3a squared minus 2. All right, let's bring it up, and we'll use these here too. These are nicely done. Now here, our x is actually in parentheses x plus h. So where the x is in that original equation, we're going to substitute x plus h. That is now squared. So we have to square this binomial. We get this trinomial. We then distribute the 3. We get this new trinomial and just negative 2. So we're substituting whatever is f of something, usually x or some other value. Here it's a, here it's x plus h. And now here is x plus h minus now, where f is just x. So what we do, notice we already have this from above, which is this here. So we're just going to write that there, and then minus what our original equation was, and this was an x, what we have here. So what happens now? Well, we have to get rid of parentheses here, get rid of parentheses here. This changes, this becomes negative, this will then become positive, and then we start grouping like terms. Well, here, this is going to cancel, and we get 6xh right there. And then we have a negative 2 and a positive 2, so these cancel. And we're just left then with this. And it's all over h. Now, the next step is, notice there's a common h in the top here. We can factor out that common h. Take a moment. Hopefully you're pausing, writing this down so you follow the protocol. And then now what can happen to the h's? Well, h over h is 1, so we can cancel it out. So this then is our final answer. Now as we look at this next portion, this is sort of critical for future math classes, such as calculus, that some of you may be moving into. So domain and codomain notation. The notation F, A arrow B, reads F defined from A to B. That sort of makes sense. From A to B. Or F maps A to B. I would have used another word here, but that's okay. It implies that F is a function from set A to set B. The symbols indicate that the domain of F is set A, And the range of F is the subset of set B. In this context, the set B is often called the codomain of F. That is your X values. All right, now let's take a look at this. A few more vocabulary as we look down here. And you'll see this as an example. But if set B is the same as set A, we use the onto B or surjective function. And we'll illustrate that as we go on. But some key words, and keep mindful of them. Now, we'll need some background information for this. It's example 7. Identify the domain, the codomain, and the range of each of the following functions. So looking at item A here, this is a funny kind of R here where it's thickened. What does that refer to? Well, this is real numbers. That is all the numbers on the number line. Now we have a funny looking Z here. What does this refer to? Well, these are the integers on the number line, and those are the whole numbers, 0, 1, 2, 3, and so on. And also their negative opposites there, opposites, -1, -2, -3. These are Z's symbol for this set of numbers. Again, R is all real numbers, Z integers. Now we have another funny looking N here. This is the symbol for natural numbers. Natural numbers, these are the counting numbers, 1, 2, 3. So you need to know that to define what's going on here. And I'll leave that up there. Hopefully you have some notes. Now, what does this say? Well, the function, and we're going to define domain, real numbers to real numbers, where something is going to be squared. Now, all real numbers, if they're squared, produce a real number. If they're negative, when they're squared, it becomes positive. So the range, or I should say the domain, is going to be from negative infinity to positive infinity, which is all real numbers. But now the range, since everything is going to be positive, will go from 0, and I should use a bracket because 0 is included in the set, and then to positive infinity. Now here, they're limiting what we have. Instead of all real numbers as what it would become, what it yields, what it maps, it's going to be this. And actually in this case, it's the very same. Because anything that is squared becomes these. Now here we have integers. And again, we're wondering which set of integers does this produce? Well, it's going to be our domain will be, we have to define this now as ... Let's say -2, -1, 0, 1, 2, ... And going to positive infinity on this side, coming from negative infinity. But the range now of this is only going to be positive integers, and that would be then, and actually I should have put this in braces, sorry about that, because this is set notation. We'll start with 0 and then go on to, now if we square 1, we get 1, but if we square 2, we get 4, and if we square 3, we get 9, and if we square 4, we get 16, and then that goes on and follows a pattern to positive infinity. Now, if we're using natural numbers here, our domain will be 1, 2, 3, 4, the counting numbers, but our range, since 0 is not one of the counting numbers, is what we have here, but doesn't include the 0. So it'd be 1, 4, 9, 16, and once you set up a pattern, you can just put the ellipsis indicating that that pattern continues. Now the book does a nice job of explaining this, and I will bring it down here so you can see the various answers. Somehow it escaped me there for a moment. There we go. Okay, let's go on. And I see I left out some important things here. Let's be sure to go over that. That in A, since the domain and the range are both the same, we can call that a codomain because they're both all real numbers. In letter B, since the domain and the range are the same, again, we can call that a codomain. And the function g, once it is resolved, is said to be onto or surjective. Let's clear that up and raise it a little. And in letter C, here the range is consistent, the square of integers, since the range is not the same. It is not, as the codomain, it is not onto or that other word, surjective. It's a word I'm not too familiar with. And then in letter D, it's not the same. It's not the same as the codomain, so it's not onto or surjective. Again, read this over, lots of detail here. I know this is running long, but these are important items. I'll shorten this, is that every once in a while when you're asked to find the domain of something, you'll find there's a variable in the denominator. Well, anything that makes the denominator a 0 has to be excluded from the domain, and that's what they're talking about here. Pause and read it. And this is our last example, and it goes over what we just talked about here. So, implied domain of a function. Determine the implied domain of each of the following functions. Okay, so what's going to limit our domain here? Well, what is under the radical sign? We can't have a value of x that would make this a negative value, therefore not a real number. So we have to exclude that. And what is the protocol for doing that? Well, you take the radicand, which is 3 minus x, and it has to be greater than or equal to 0. Because the lowest value you could have under that would be 0. Can't have any negative values. So we have to solve for x. Well, just transpose the x. Becomes positive on this side. And now rewrite it. X is going to be less than or equal to 3. So you can't have any value less than that. So the domain here is, and I've raised it up so you can actually see the answer, is this. This is the algebraic notation. In interval notation, it's going to be from negative infinity to 3 with a bracket, and that's what they're showing. And you might say, how could you have all these negative values here? Well, because x is negative. So when you go the opposite of a negative, it makes that positive. So all of these eventually become positive under the radical sign. All right, let's go on to the last one now. And I'll clear this up. And here in our denominator, we have x squared minus 1. And if we equate that to what would make this 0, this actually factors, because these are conjugates here. Difference of perfect squares factors into their conjugates, x plus 1, x minus 1. So values that would make this denominator a 0 would be a negative 1 for this one or a positive 1. So in writing this in interval notation, we would say we have to exclude these values. Let's put it on a number line. And it would look like this, that over the negative 1, there'd be a hollow. Negative 1 has to be excluded, as does positive 1. Now, how would you put this in interval notation? Well, it's coming from negative infinity, going up to negative 1. We're going to use a parenthesis because negative 1 is not included. And then this is in union. We're using the union symbol. And on this side, it starts the other side of negative 1, goes up to a positive 1. Again, a parenthesis because the 1 is not included. And then in union, starting with a positive 1, the other side of positive 1, going to positive infinity. And I believe this is what they will show us down below. Good job. Okay, this was rather long one, lots of background material, and of course you'll be doing your practice and your certify.